10 people going on a weekend trip together can very quickly generate a dense web of overlapping IOUs. Every time one person covers a shared cost, they create a directed debt relationship. In a closed group, these connections don't scale linearly with the number of users, they grow geometrically. In a worst-case scenario where every person owes every other person, the system must account for n times n-1 potential connections. For a group of 10, that is 90 separate directed debts. Traditional ledger systems struggle with this volume because they are designed to process and record every physical transaction as a permanent, independent event. Enterprise applications like Splitwise aim to collapse this O of n squared complexity, prioritizing a final settlement map over a raw archive of every transaction. The engineering goal is to reduce this chaotic web into an O of n map where the number of payments required to settle the group never exceeds the number of participants. Building a system that can do this reliably requires 3 distinct layers. 1. Data modeling. 2. Algorithmic routing. 3. System architecture. These 3 layers coordinate the transition from a messy input of receipts to a finalized, simplified payment plan. At this scale, managing shared debts becomes a challenge of network flow and distributed system design. The process of simplification begins by discarding the specific history of who originally paid whom. Instead of tracking edges between people, the system collapses all incoming and outgoing debts for an individual into a single integer, their net balance, or B of V. Because the money is moving within a closed group, the sum of all individual balances is always 0. This creates a network with 2 distinct states. Nodes with negative balances are debtors, while those with positive balances are creditors. Any user with a balance of 0 is already perfectly settled and can be removed from the calculation to prevent them from acting as an unnecessary routing hop. This abstraction leaves us with a flattened dataset that is ready for algorithmic routing. Converting emotional human debt into a sterile data array makes the problem mathematically solvable. To connect the red debtors to the green creditors, we model the settlement as a flow network. We initialize this network using 2 artificial bounding nodes, a source and a sink. The source connects to the debtors, capped by the amount they owe, while the creditors connect to the sink, capped by the amount they are owed. Between them, we draw internal routing edges with infinite capacity. We then apply a max flow algorithm, such as Ford-Fulkerson, to push theoretical money from the source to the sink. The algorithm searches for any available path through the network and pushes as much volume as the edge capacities allow. The problem is that a greedy choice made early in the process might block a more efficient global path discovered later. To fix this, we use reverse edges. These allow the algorithm to effectively undo a previous flow assignment if a better route is found. These are not actual financial refunds, they are computational permissions to overwrite suboptimal routing logic. The algorithm repeats this process until no more augmenting paths exist between the source and the sink. When we remove the artificial source and sink, the remaining non-zero internal flows reveal the final settlement map. Achieving system-level optimality requires the ability to continually refine these routing decisions until maximum capacity is reached. Max flow algorithms perfectly minimize the volume of money moved, and they do it in polynomial time. However, minimizing the total number of transactions, the actual goal for the end user, is a much harder problem. Calculating the absolute minimum number of edges required to permanently settle a large group is computationally intractable for modern computers. This complexity is well documented. The calculation for a minimum transaction set is an NP-complete variation of the subset sum problem. For a server processing thousands of groups simultaneously, searching for a perfect mathematical optimum would lead to a total performance collapse. Instead, production systems use greedy matching heuristics to find a good enough approximation. This approach ensures a reliable ceiling. Any group of n people can be settled in at most n-1 payments. In professional engineering, theoretical perfection is often traded for reliable sub-second execution speeds. To see how this works in practice, we have to look at the physical constraints of production hardware. Running these graph routing computations over millions of interconnected nodes is a CPU-intensive task that requires significant memory bandwidth. If these calculations ran on the primary database server, they would block the incoming stream of user transactions. The solution is a phase-splitting scheduling model that separates these workloads. The relational database handles the lightweight transaction logging, ensuring every expense is recorded with ACID-compliant integrity. A decoupled compute pool periodically pulls that raw data to execute the heavy graph traversals in the background. This simplified map is then cached and continuously updated as new data flows in from the primary database. On a global scale, standard data entry and complex graph reasoning are incompatible workloads that must be physically isolated. This is the journey of a single dinner bill entering the system. It is first logged as a permanent truth in the relational database. Background worker nodes then strip that truth down to a zero-sum net balance array. Finally, the flow network algorithm calculates the optimal routing and delivers a simplified N-1 settlement map back to the user. The brilliance of debt simplification lies in its willing suspension of reality. It ignores how physical money moved, abstracting financial chaos into pristine network logic.